In this demo, I will walk through the Azure Machine Learning tutorial Distributed PyTorch Image Classification. This tutorial is a great way to run your first distributed PyTorch training job and familiarize yourself with the Azure Machine Learning SDK prior to running your own jobs. Let's jump over to the console. So here, we're starting this tutorial again directly from the Azure Machine Learning workspace that we created on a previous step. In this example, we're going to be running this distributed GPU training tutorial right here. So there's a couple different ways that we can navigate to this tutorial. The first is to go ahead and hit that start button. And you can see here it opened up the notebook section here and under samples. So you can see here your kind of all of your user files within the shared file system that's backing. Taking a step back, going one level deeper on Azure Machine Learning, when you create the storage account with your Azure Machine Learning workspace, you have kind of a blob storage container that works for, all different kinds of files, including training data. What also gets spun up is a shared file system that's kind of backing all of your development environments within Azure Machine Learning here. So it enables you to share code and collaborate with others using this shared file system behind your workspace. So there's a couple different ways you can do this. You could clone just this notebook file over from the samples here over into your shared file system. Or alternatively, what you can do, if you plan to run through multiple of these tutorials, is you can actually go to this SDK v2 section and clone the entire folder over here like I've done here. And so in this case, we're going to navigate to this tutorial. It's going to be under the tutorials folder, end-to-end distributed PyTorch image folder. And this is kind of the walkthrough notebook that I'm going to open up here in a sec. I just wanted to call out a couple other things within this tutorial. You see requirements.txt that shows all the kind of library dependencies needed here for this tutorial. And within this SRC folder, you also see this PyTorch DL train folder, which contains the actual training scripts. So both the model.py for defining the model, image.io. So this is a file for some image processing utilities, profiling for setting up things like TensorBoard, and in this case MLflow with this tutorial, and then train.py, and that's actually what gets called and executed when you kick off your training job. So let's go ahead and open up the tutorial image, or sorry, the tutorial notebook. Prior to executing this notebook, you're going to need to create a compute instance to be able to run it. So up at the top here, probably the fastest way to do this is go ahead and you can see here, I do have a AML Italy North instance that I had previously created that's already up and running. And actually up here, you can also see various different kernels associated with this notebook. So in this case, I'm running a Python 3.10 kernel, but you can see there's different kind of PyTorch and TensorFlow kind of kernels in here that are pinned to different Python versions. All right, so in this case, if you go ahead and create a compute instance here, I just recommend, in this case, I'm running a memory optimized instance. I have tested this on the general purpose instance, and this should be fine as well. The memory optimized, you should be able to execute this tutorial as well. In this case, I was doing a couple other things on this compute instance, so I opted for the larger memory optimized. But for the purposes of this tutorial, we're creating a separate remote GPU cluster, so we don't need a GPU virtual machine for executing the commands against our GPU cluster. So any one of these three should be sufficient to run this tutorial. And actually, if we just click through the wizard here, I just wanted to call it, there's some additional settings in here for Azure Machine Learning Compute, which can be handy for development. There's kind of the ability to enable auto shutdown after a certain period of inactivity. You can also add kind of custom schedules here for your team as well. There's, for example, if you were going to do um, more actual development on this instance, you could set up SSH access for debugging. Um, some other features to call out here. You can also start up specific applications here. So long story short, this is a great development environment. There's a number of features in here in addition to this compute that make it a very friendly development environment. So in this case, we'd already created compute here. I did actually want to call out here, we covered in the training videos previously, but you do have the ability to launch to create VS Code web-based versions as well. So you could use that to run through this tutorial as well. One of the benefits of doing that, in addition to kind of running it in Azure Machine Learning, is you can access it via the browser. So it gives developers a lot of different options for development. And within VS Code, there's also additional advanced development features like you could have GitHub Copilot, for example, that's in that VS Code instance here. So there's a lot of additional developer tools that you can layer on top with VS Code here, in addition to this notebook experience. And actually separately, um, you can also launch a tutorial in a local version of VS Code as well. All right. So to start out with this tutorial, what we're doing here is we're going to launch a data preparation job, and then we're going to test and run a multi-node GPU PyTorch job. And then you'll see, as I called out with this profiling.py script, there's also integration with MLflow for analyzing your training metrics after as well. So the first step in this tutorial is we're going to connect to the Azure Machine Learning Service. So we're going to create a client here. And so it's going to provide, you need to provide metadata on your subscription, your resource group, workspace name, and go ahead and run these particular cells. Now, up at the top here, these are two examples of using the Python SDK to create compute resources. So in this case, both of these are going to be multi-node compute, a multi-node CPU cluster for data processing. So in this case, manipulating images to get them ready for training. And so you can see some of the syntax I'm doing here. I'm going to jump down to the creation of the GPU cluster because this is probably a little bit more pertinent to your guys' workflows. So you can see here, this also uses the Azure ML Python SDK for defining a compute cluster. So, previously we looked at how to navigate or create a compute cluster from using the UI from the compute ribbon. In this case, we're doing it via the SDK. So you're providing a name here. The top level object that we're going to be importing here is from Azure AI ML entities. So for AML compute, and we're going to be defining the name of our GPU cluster. And in this case, you would update this tutorial to be the GPU cluster SKU, so that multi-node A100 VM. Like we saw in the UI, you can specify the scaling up and scaling down parameters, as well as the idle time here. And by using our client, we can trigger the creation of this cluster with the begin creator update method here. And this top one here, you can see there's two different data sets we can download for testing here. In this case, I've opted for the smaller data set for testing here. So this is actually a command job for data processing. So um, this is going to be targeting our CPU cluster that was defined above. And what it's going to be doing is it's going to be downloading um, data set of dog images and some of the common elements that we saw from previous training videos. You're providing display name, kind of this command for unzipping and unzipping the input data set and then outputting it to a specific Azure Blob Storage directory for training. And so all of the key elements are here. We're defining kind of our environment. So this is going to be our environment container. We're specifying our compute target, and we're specifying both our inputs and outputs to our job. So there's some utilities directly in this tutorial for monitoring the status of your job while it's executing. This data pre-processing job takes anywhere from 3 to 5 minutes here, and you'll see it displayed under the job ribbon. So before we jump over to the job ribbon, I just wanted to go a little bit further in the tutorial here. So there is an option to download a second larger data set for training as well. And this is probably the most important part of the tutorial. It's defining kind of a multi-node PyTorch GPU job. So like we saw in some of the previous training videos, I wanted to walk through defining this command job here. So there's a couple important entities here. First is going to be, again, that kind of command wrapper job. We're bringing in kind of inputs and outputs. Recall that the Azure Machine Learning Data Service uses both typed inputs and outputs. So we'll use that to specify paths to our remote input data. And in this case, from the previous job, we actually brought that data set into Azure. So in this case, we're going to be using it to specify Azure machine learning paths to specific storage or data set repositories. And under this kind of entities object here, we're also importing some objects for defining retry settings, as well as specifying the topology of our distributed training configuration as well. All right, so in the command job, up at the top, we have some. So we covered imports, and up at the top here, I did want to cover kind of the metadata as well. So here we're defining our experiment name, kind of a more friendly display name, and a description of our model job. We're specifying with kind of our code and command arguments here, a path, in this case, to a local code folder here, this PyTorch DL train, that we're going to zip, and then ultimately is going to be what gets copied over to the instance and executes once we submit this job here. So this train.py here is what's getting called in this command argument here on the Linux operating system of our compute cluster. And here, just like we would if we're running a script locally here, we're specifying command line flags here that allow you to, change the default behavior of our scripts without modifying the code here. So in this case, we're pointing at paths to our training and validation data sets, as well as passing in some of our command line input variables, so things like batch size, prefetch factor, model architecture. So the way that we would specify some of these environment variables in at runtime to modify our script's behavior is going to be in this input section here. So again, we have these typed inputs. These are ultimately Python dictionaries that provide a path to kind of this Azure ML data store here for our training and validation data sets, specifying its type. In this case, we're specifying download. So, we have these really large memory GPU cluster instances that we're going to be running this training against. So in this case, this data set's quite small, so we're going to opt for download. So it's going to copy the raw data sets from um, these Azure data stores directly over to our instance prior to training. And let's see, here we have kind of our output configuration here. So in this case, you can see this is just an example of upon completion of the training job, just for illustrative purposes, I've shown how you could specify an output data location. So in this case, at completion of the job, it's copying the data set that we copied over in an instance back to the blob storage associated with our workspace here. So this is just for illustrative purposes. And you can see here, in this case, I'm just showing kind of a mount mode, so it's going to stream that data set back to Azure Blob Storage. The next line here is the environment. So in this case, this is specified in Azure container for PyTorch environment with PyTorch 2.2, along with the associated kind of CUDA version pinned to that. And here we're providing the name of our GPU cluster compute. So this name here needs to match what we the name of the compute cluster that we created above. This line shows kind of the implementation of configuring the job retry settings. And here is kind of our this kind of shows our distribution configuration here. So I mentioned that there's 3 supported distribution frameworks for Azure Machine Learning. There's PyTorch, TensorFlow, and MPI. So what we're doing for this specific example is we're configuring the topology for our distributed GPU training job. So we're specifying the number of instances. So in this case, we want our job to run against both both nodes that we deployed in our previous GPU cluster. And one thing that's a little bit different here that I sometimes get questions on is the way that PyTorch distributed training works on Azure Machine Learning is a little bit different than MPI, for example. So in this case, this process count per instance here, for MPI, you might set this to the number of GPUs on the instance. In this case, the way that PyTorch distributed training runs is we're specifying that we're going to have one process running on each GPU on the node here. So this will ultimately span out to the GPU cluster instances have 8 GPUs per node. And so in this case, we're running across 2 nodes so that there's 16 total GPUs that are specified here. But this process count per instance for PyTorch is just specifying one process per GPU running on that node. MPI, for example, a different distribution framework, you can set and have multiple processes running on a single GPU. So that's an option with other frameworks. In this case, this is what we recommend for PyTorch in particular. All right. So that kind of specifies kind of the definition of our training job. And just like we did with our data preprocessing job here, we're going to use our client and then run a creator update for this training job that we specified above here. And there's some utilities here. So once you run this cell, is what will actually trigger the job. And you can see a couple different steps that are taking place here, but specifically you can see here it's copying our local code folder, this PyTorch DL train, over to the instance to start our training job. So you can track it here. Um, if you're developing here and you want to track the status of your jobs, you can also go over to the jobs ribbon here. And so you can see here, I got a um, couple different jobs, for this tutorial that I've run against here, but you can see here in the experiments tab here, um, this experiment corresponds to our image preprocessing job that we launched on our CPU cluster here. And I'm going to go back and look at our GPU cluster job. So then you would see a separate experiment, which is an organization of all the runs of against your CPU cluster and your GPU cluster. So this end-to-end image sample here has all the runs against our GPU cluster here. Let's look into and actually one thing to note is I executed two jobs against the cluster for a specific reason. So the initial job takes when you trigger that takes a little bit less than 8 minutes. But you note on subsequent runs, the training time is about half of that. And that reduction in training time is because the PyTorch environment image that we're using gets cached in our container registry between subsequent runs. So, it's significantly faster for subsequent runs because your environment image is already kind of built here on the instance. All right, so if we click on this example here, you can see quite a bit of metadata here. You can see kind of our compute target here. You can see metrics related to training directly summarized up here. Some of the input parameters that we passed in at runtime to control our job script here. And let's see, probably most pertinent is going to be output and logs up here. So you can see, I mentioned there was, we were targeting this job against 2 instances with 8 GPUs on it each. Each GPU has a kind of corresponding log for troubleshooting associated with it. So for standard out here. And so you can open this for each individual GPU, and you can say the training progress that's taking place on each one of it. There's also monitoring here. So this is probably one of the most useful tabs here for monitoring the performance and ensuring that you're maximizing GPU utilization when running your jobs against the cluster. So you have kind of your InfiniBand metrics for your throughput for each individual node. You have things like disk usage. This is probably most pertinent if you're well, actually, in download or mount mode, disk usage is important to monitor to make sure that you're not filling up the disk, and which can result in unhealthy nodes on the cluster. There's additional metrics around data reading as well. You can track your GPU memory usage as well, and you could see in this case, this is an example, and you can see all your kind of summary metrics over the course of your job at the top here. In this case, this is an example where we were using an extremely small data set, and we were probably over provisioned on compute needed for this job. So we didn't need 16 GPUs to process this job here. So it's accounting for the low GPU utilization here. But based on some of these metrics here, things that you might do to improve your utilization here might be increasing the batch size of your scripts. If you're seeing this low CPU utilization, you might want to increase the number of workers there to prefetch more data so your GPUs aren't sitting around data starved. So that could be a couple different things that you'd look to maximize utilization here. You might also make sure that that there are any issues on the network side as well. And yeah, this might be an area where, maybe you would update some of the networking environment and variables to kind of tune here. But across the board, this is a great starting point once you're triggering jobs against to um, maximize kind of your data access, kind of your data loading for your jobs, um, the compute efficiency of your jobs, as well as some of the networking behind that as well. So with that, I'm going to jump back over to tutorial here and just conclude by showing there's some additional sections here showing how you can use MLflow to connect back to your experiment results here for again pulling a lot of those training metrics, your accuracy, your loss curves, things that are directly up here in your workspace or that we saw in kind of in the job metadata. You can pull that directly into here for further analysis and plotting and manipulation. So it's been quite a few startups that have used MLflow on the GPU cluster. Some popular alternatives have been weights and biases and Neptune as well. The various startups have preferred here. So um, MLflow probably has the most integration, but both weights and biases and Neptune are great options. I think the most important takeaway there is definitely use an experiment tracking product to make the most of your GPU cluster reservation. And with that, that concludes our tutorial on running your first distributed PyTorch training job on the Microsoft for Startups GPU cluster. With that, I hope you have the confidence to get started training on the cluster. And in subsequent demos, we'll look at some additional ways to troubleshoot this compute using Azure Machine Learning. Thanks and happy building.